Hello, Wellesley High School. Today we're going to talk about electron configuration, specifically orbital notation. In the diagram below, you see a list of the orbitals in an atom. Remember that an orbital is the quantum mechanical way of organizing electrons within an atom. Okay, they're areas of electron density, so areas where electrons are likely to be found, organized based on energy levels. Okay, these orbitals are listed from lowest in energy at 1s to highest in energy at 7p. Okay, so there are a few things I want you to notice about this diagram. Okay, the first of which is to look for the pattern of the boxes. Okay, notice that every single time we have an S, okay, it doesn't matter what the number is in front of it, right? 1s, 2s, 3s, 4s, 5s, it's always one box. Okay, so the S subshell comes with one orbital. Okay, so S's come in sets of one orbital. The P's, on the other hand, so if you look at 2p, 3p, 4p, 5p, etc., notice that the P's always come in sets of 3 orbitals. Okay, so the P subshell comes in a set of 3 orbitals. Okay, and then notice the D's come in sets of 5, and the F's come in sets of 7. Okay, each one of these boxes, each one of these orbitals can hold a maximum of 2 electrons. So if we think about any S subshell, it can hold a maximum of 2 electrons. P subshells can hold a maximum of 6, D subshells can hold a maximum of 10, and F subshells can hold a maximum of 14. Okay. The only other thing I need you to notice from this picture is the order. We need to notice the sort of where it gets funny. Okay, so here we go from 1s to 2s to 2p, that makes sense, 3s to 3p, and then notice here 3d is sort of out of order, right? We go from 4s to 3d to 4p. Okay, so the d's are basically always behind 1. Okay, so d's are always a little bit off. And then notice up here we go from 6s to 4f. Okay, so the f's are off by 2. Okay, this will make a little more sense once we look at the layout of the periodic table, but I just wanted to point those out as sort of anomalies in the order. Here's a summary chart of some of the information that we just talked about. So again, this is subshell, number of orbitals, so number of boxes, and then the maximum number of electrons. Okay, so the S subshell has 1 orbital and can hold a maximum of 2 electrons. P comes in sets of 3 orbitals, so it can hold 6 electrons, okay, and so on. Notice here that this is maximum of number of electrons. This doesn't mean that every single time we have a P subshell, it's going to have 6 electrons. It can just hold a maximum of 6 electrons. There are 3 main rules for doing electron configuration or orbital notation. Those are the Aufbau principle, Hund's rule, and Pauli exclusion. Okay, the Aufbau principle tells us that we have to fill in the lowest energy orbital first. Basically what the Aufbau principle tells us is the filling order, okay, as shown below. Okay, so this is the filling order. Again, 1s, 2s, 2p, 3s, 3p, and so on. This is the same exact order as in the diagram at the beginning of this video, but just listed in a different way. And again, on the next slide, we're going to go through how to see this order on the periodic table. So there's no need to memorize this. Hund's rule relates to orbitals that are the exact same energy level. Basically, when you have a set of 3, 5, or 7 orbitals at the exact same energy level. So if you remember from our diagram, we listed the orbitals in order of increasing energy. All 3 orbitals for the 2p, 3p, 4p were at the exact same energy level. So Hund's rule basically tells us that electrons are going to spread themselves out at the exact same energy level as much as possible. Okay, so for example, if we have a 2p subshell, so 3 orbitals, we're going to fill electrons 1 in each before doubling up. Okay, so I would place 1 electron in each orbital before doubling up. Okay, so adding that 4th electron will cause 2 electrons to occupy the same orbital, but before that the electrons spread out as much as possible. I like to think about this as the bus rule. Okay, so if you're getting on a city bus and there's a completely open seat, or there's a seat next to a crazy person, you'd want to sit in the completely open seat rather than next to a stranger. Okay, just sort of natural. Electrons exist in the exact same way. Okay, and then finally is the Pauli exclusion principle, which I've already sort of hinted at here. Basically, if 2 electrons are going to exist in the same orbital, they need to have what are known as opposite spins, and basically the way we represent that is by drawing 1 electron as an up arrow and 1 electron as a down arrow. Okay, so the Pauli exclusion principle is basically just the way for electrons to exist in the same orbital, and we represent it as a 1 up and 1 down arrow. So as promised, you are not going to have to memorize the filling order as long as you can read it on the periodic table. Okay, this picture shows you the different areas. Okay, so notice that there are sort of blocks on the periodic table. So if you look in the first 2 columns, you see these are all S's. Okay, this is the S block. Okay, including helium. Okay, so all of those atoms, all of those elements have valence electrons ending in an S orbital. Okay. Next is the P block. Okay, over here. Okay, sorry my coloring isn't so good, but the P block is over on the side. Okay, the D block is in the middle. Okay, and then the F block is down at the bottom. Okay, so from this version of the periodic table, you can basically predict what orbital the valence electrons are going to end in. So in the first row, we have 1s. In the second row, we have 2s and then 2p. Then the third row, we have 3s and then 3p. And then the fourth row is where it starts to get a little bit weird. Notice we start with 4s, but then we go to 3d. And if you remember when we were looking at the energy diagram, I pointed out that 4s is actually lower in energy than 3d. So 4s is filled before 3d. Okay, and luckily 4s comes before 3d on the periodic table. Okay, after 3d we have 4p, and then 5s, 4d, 5p, 6s. Okay, after 6s, the periodic table goes down to the bottom. Okay, so the periodic table goes down here. Okay, so we go from 6s to 4f, then we jump back up to 5d, okay, and then 6p, and so on. Okay, in theory, the orbitals keep going, okay, but these orbitals that we've covered are enough for all of the elements that currently exist. Okay, so these are the only ones we need to worry about.